Welcome everybody to IEEE's Computational Intelligence Society's webinar. This one is hosted by the Government Activities Committee. My name is Robert Stewart and I am presently the chair of that committee. What we're really all about is raising awareness about computational intelligence and particularly governmental interactions with that. It can be government interactions like with R&D, whether it be technical progress or programs. It can also mean governments. How are we governing AI here in the US and where we're at today and globally, education, and so on and so forth. So any sorts of things like that we are interested in talking about. And so I'm honored today to have with us Dr. Prasanna Balaprakash, who's the Director of AI Programs at Oak Ridge National Laboratory. Oak Ridge National Lab is a large DOE national laboratory in the Southeast United States. Prasanna, thank you for being with us today and sharing your time from your busy schedule to give us some of your thoughts and perspective on it.
Thanks for the opportunity, Robert.
I was looking a little bit today at the ORNL website. So for folks that may not be familiar with ORNL, go to ornl.gov and take a look at all the things that are going on there. It's extraordinary. Everything from neutron sciences to environmental sciences, manufacturing, energy securities, climate impact change, national security, certainly AI. It's extraordinary. Prasanna, I think it's I think there's 6,000 or more employees there now, and about a $3 billion budget. So a lot of resources to get things done. Yeah. I imagine as the director of AI programs there, you are quite busy in all those intersecting science lanes. So thank you again for joining us today. So why don't we go ahead and get started with a normal sort of bio introduction. And Prasanna, if you want to just bring your slides up while I'm doing this, that'll be great. So Dr. Prasanna Balaprakash is the Director of AI Programs and a distinguished R&D scientist at Oak Ridge National Laboratory, where he directs laboratory research, development, and application of artificial intelligence and machine learning to solve problems of national importance. His research interests really span the breadth of AI ML, from optimization and high-performance computing. He is a recipient of the U.S. Department of Energy's 2018 Early Career Award. Very impressive. Prior to joining Oak Ridge, he was a computer scientist, lead computer scientist at Argonne National Laboratory. He earned his PhD from I'm sorry, Prasanna, if I mispronounced this, Dakota Iridia at the University Libre de Bruxelles, where he was a recipient of the European Commission's Marie Curie and Belgian FRS Aspirant Fellowships. That was a mouthful. Very impressive, though. So I will stop talking and get out of your way, Prasanna. Take it away.
Thank you, Robert. Thanks for the invitation. And also thanks to the IEEE CIS for giving me this opportunity. Today, I'm really excited about the ORNL, talking about ORNL's AI initiative, advancing secure, trustworthy, and energy efficient AI for scientific discovery. Little bit of introduction on DOE National Labs. These labs were born out of Manhattan Project, now lead research in energy, security, and advanced technologies. What you see here is a map of different national labs, and they are color-coded based on their mission. These labs are grouped into science labs, energy labs, national security labs, and environmental labs. And it is the headquarters, the DOE headquarters is in Washington, D.C. And as you can see, Oak Ridge is a science lab, which is color-coded in green, but also has a very significant national security presence. This is reflected in ORNL's mission. The ORNL's mission is to deliver scientific discoveries and technical breakthroughs needed to realize solutions in clean energy and national security and to provide economic benefit to the nation. This is reflected in every aspect of research and development that we have in the lab. Coming back to AI, specifically AI for science, ORNL has a very rich history in leveraging AI for science. What you see here is a timeline of AI. Starting from 1940, we had the birth or the dawn of AI with the birth of Turing tests, and there were several rule-based, expert-based systems around 1970s up to 1970s. And then we hit the winter because these systems were not scaling up. And during that time, there is also towards the end of towards the end of 80s and beginning of 90s, we had this new era of AI, which is called machine learning. Here, the idea is to learn directly from the data as opposed to rules or the humans developing rules and experts coming up with the different types of rule-based systems to solve problems. This was transformational in AI. And in 2000, we have onset of generative AI and all the sort of the new new ideas in AI for scaling up, for tackling large amount of data, to learn from large amount of data, and everything sort of happened around that time. In 2020s, we are already talking about various ethical aspects of AI, which means AI is profound, prevalent, and it's everywhere. It's already affecting our lives. At ORNL, the first AI project was started in 1979. It's called Oak Ridge Applied AI Project. 1981, there was a review article in Oak Ridge Review magazine where there were projects on AI infrastructure to support spectroscopy, environmental management, nuclear fuel reprocessing, and programming assistance. During the AI winter, the focus was on robotics, primarily various types of humanoid robots or robots that interface with computers to perform actions. And then the attention went to automated machines for environmental management and so on and so forth. In 2017, we had the world's smartest supercomputer optimized for AI. It's one of the earliest supercomputers that used graphical processing units, GPUs, from NVIDIA. Although the machine came in 2017, the decision to go for GPU computing happened in 2012, which means the research for that happened in 2010 because at that time, the supercomputers, which primarily based on CPUs, were not powerful enough to do scientific computation. So DOE and Oak Ridge National Lab, they started exploring this gaming hardware, graphical processing unit, to do scientific computation. And at the same time, AI was emerging, machine learning was emerging, and there were a lot of computational needs for developing AI models. So all these things happened more or less at the same time, which eventually led to what we call the new AI revolution, powered by large amount of data and large compute. Today, we have Frontier. It's the first exascale machine for open science. It exceeded exaflops, that is 10 to the power of 18 floating point operations per second. And in mixed precision, which is relevant for AI, it can perform 10 exaops. It used to be number 2 on Green 500 because of the energy efficiency. And we have used this machine to scale AI models up to trillions of parameters. It's very, very capable. AI is transforming science across Oak Ridge National Lab, across TUI, across nation. At Oak Ridge, starting from spallation neutron source all the way up to high flux isotope reactor, these are very specialized, very large experimental facilities. AI is transforming science. To perform science, to conduct experiments, to come up with better experiments, to analyze large amount of data, and also improve operations at these facilities. A key example is AI at Oak Ridge Leadership Computing Facility, which hosts the Frontier supercomputer. The supercomputer is primarily designed for large modeling and simulation workloads. Now we are using AI to reduce the computational expense of computational expense of these large scale simulations. We are talking about 100x to 1000x speedups on these kind of very large simulations. That is very transformational. Imagine we can run climate simulations 1,000 times faster than what it is today. We can do better proactive analysis and look at various types of risks and so on and so forth. It's game changing. It's really, really transformational. Despite all these promises, we are facing a number of challenges to make AI truly, truly transformational. The promise of AI is challenged by safety, security, trustworthiness, and energy efficiency. For example, hallucination is the dictionary.com word of the year in 2023. This means that the AI models, the more powerful model is, it can make up facts which are not real. In a recent Nature review article, it was shown that it was discussed like in how scientists are impressed by the latest ChatGPT model o1, but at the same time they acknowledge that it is hallucinating more than its predecessor. So the trustworthiness is a major concern with powerful AI models. Related to that, it's also the energy efficiency. If the current trend of AI model training and inference continues in data centers, in AI data centers, the amount of energy needed by these data centers alone will be almost 1/3 of the total US energy consumption. This is huge. We have a moral and ethical responsibility to address the energy aspects of AI. It is not surprising that the White House last October 2023, came up with this executive order on safe, secure, and trustworthy development and use of AI. Government didn't ask us to build the most powerful model ever, but they asked the community to really think about the safety, security, and trustworthiness of AI. It is easier said than done. These are really challenging problems. These are the challenges faced by AI in the next decade. The paradox of AI development are many. For example, in AI, it is easy to demo, but it's very hard in production. We can write quickly, code in Jupyter Notebook and show the model is training and so on and so forth. But when it comes for deploying that model in real time, it's a completely different ballgame. There are so many different complexities associated with that AI model deployment. In many cases, hard problems are easy and easy problems are hard. So it is important to understand what are the classes of problems that AI can solve. AI is not a hammer that we can use for all different problems, to solve all different problems. And even within AI, there are different types of models. Generative AI, although received a lot of attention in recent months, it's not the go-to approach for all the problems. There are predictive models. There are much simpler models that can solve problems much more effectively. So it's important to understand what the strengths and limitations of different AI techniques. And for some problems, AI is not even a right choice. So it is important to take all these factors into account. There is ever-growing open research problems. The more complex, the more sophisticated, the more powerful AI models that we build, the more problems that we are seeing, the more open challenges that we are encountering. Hallucination being one key issue, explainability, transparency, and all other things, right? So more complex the model is, it's very hard to make assessments about these important aspects that we humans care about. In many cases, humans remain a roadblock because it is important to validate and verify these models. In a typical software setting, we know what the software is about. We can read the software, we can read the lines, we can read the code and understand and what is happening in the code. Right? However, when it comes for AI models, we don't know what is inside. And because of that, validating and verifying AI models are a big challenge. And often this challenge is pushed on the humans, and we need to find a way to validate and verify these models. These are very, very challenging tasks. There are unique challenges with cyber physical systems, right? So there's one thing about AI model sitting in a laptop where we interact with that model and getting answers for the questions that we have. But when it comes for AI model driving experiments in a big experimental facility, opens up completely new set of cyber physical challenges. We have to be absolutely sure that this model will not make mistake. This model is secure so that it's not open to cyber attacks. Data poisoning, model poisoning, and all of the things come into play. So these are all different challenges when it comes for responsible AI development and deployment. AI development is multifaceted. It's not about achieving accuracy. We have to develop methods to establish trust in AI systems. We have to deal with fairness, privacy, transparency, robustness. And many times, these metrics, we have to pay a price. And often that price is energy. So how to make these models more energy efficient without losing all other aspects that we have in front of us, depending on different applications. Again, I want to emphasize the fact that accuracy, although driven primarily by all the benchmarks out there, is not the only metric. When it comes for deploying a model for common use, we need to make sure that the model is fair. The model does not leak private information. The model is transparent to the end user to make sure that what the model is about, and also for the developer, and also for the policymakers, and so on and so forth. So there are many different aspects with AI development and deployment, and that makes AI challenging and also fascinating. ORNL's AI initiative that we have in the lab is a lab-wide cross-cut effort that focuses on advancing secure, trustworthy, and energy-efficient AI. It has two axes, application axis and foundation axis. In the application axis, we have AI for scientific discovery and complex systems, AI for experimental facilities, and AI for national security. On the foundation axis, we have secure AI with focus on alignment, cybersecurity, and robustness, trustworthy AI, validation verification, uncertainty quantification, and causal reasoning, energy efficient AI that focuses on scalability, edge, and novel AI hardware. These are not mutually exclusive. Depending on the type of application, we have to mix alignment with validation and verification at the edge. For different application, we have to focus more on cybersecurity with causal reasoning and scalability, and so on and so forth. So depending on the type of science use cases and national security use cases, we have to come up with a different mix between the foundational methods. And these foundational methods advance the applications. The applications inform what type of foundations that we have to develop. A topic that we are very, very excited about is foundation AI models. In a typical setting, what people usually do is take a data set, develop a data set specific, domain specific model, and use that model for predictive performance, to predict something, and use it for certain downstream task and call it a day. A foundation model is different from domain specific model. A foundation model is a model where we take a diverse set of data sets that span across multiple domains, that span across multiple modalities. We are not just talking about text. We're talking about text, images, time series, point clouds, graphs, and so on and so forth. We're not just talking about Wikipedia articles. We are talking about scientific articles. Um, data from materials, chemistry, computer science, fusion energy, and so on and so forth. DOE is the world leading producer of diverse scientific data. We want to leverage that data and build what we call foundation model across all these data sets. And not necessarily a single model, but a class of models. One can think of a class of models, what we call foundation AI models. Then once we have that sort of base foundation model, which requires, of course, large compute to do that. Once we have that foundation model, we can take that model and adapt it for various types of downstream tasks. One example here is a multi-scale foundation model for computational fluid dynamics. If we have such a base model for computational fluid dynamics, we can take that and do that for, and then adapt that for modeling and prediction, weather-related applications, future extractions and control, design optimization, system identification for a wide range of computational fluid dynamics applications. There are many advantages to that, right? So one is in many domains, we don't have data. As such a base model can allow us to transfer knowledge from one domain to another domain. And then the other advantage is what we see in the language models, the so-called emergent capabilities. Emergent capabilities are capabilities which are not part of the training data, but the model will be able to correlate between different modalities, different domains, and come up with new knowledge. And for example, correlating between materials and chemistry and climate, and use those knowledge for accelerated design, right? So this is unheard of, right? So this opens up really new avenues for scientific discovery. And we can use such a kind of things in hypothesis generation, digital twins, inverse design, optimization, accelerated simulation, autonomous experiments, right? So it's not that one model that can do many different tasks, one model that know many different science domains, one model that can operate on different types of modalities, text, images, time series, and so on and so forth. That is a very powerful paradigm. To that end, we started with developing basic functionalities, basic capabilities to train foundation models. So such foundation models are very large and they cannot fit in a single GPU memory. So we need to find way to take that model and chop that into smaller pieces and distribute that across multiple nodes of a very large supercomputer and train that model in a distributed and in a parallel way. We have advanced this technique by doing this distribution of model across multiple GPUs. We improve the performance, and we have developed new class of parallelization techniques. For the first time, we did that on non-NVIDIA hardware. So many of these large language models are primarily done on NVIDIA hardware, but this is the first time because Frontier machine that we have is a AMD hardware. So we have to customize the software stack. We have to come up with different types of parallelization strategies that take into account the architectural aspects of AMD. So this is the first time such a large model training was done on Frontier, on non-NVIDIA hardware. We have achieved more than 80% accuracy. This is the best use of hardware and thus energy efficient. And more importantly, we have democratized the recipe for the benefit of scientific community. So we made this software open, and anyone who can get access to Frontier now can go and train such large models, large foundation models. And this is a press coverage of our work where they highlighted how we trained such large model on Frontier. In fact, we took only 3,000 GPUs to train a trillion parameter model, which is just 8% of the entire machine. We didn't train it to to completion. This is a large language model training, but our focus was primarily to develop the capability to train large models and make it available for everyone. Using that capability, now we are transforming various scientific domains. The first one is material science. Material science is one of the common theme across all DOE labs, starting from battery research all the way up to coming up with a better quantum material for quantum computers. Everything is material science. And one of the key challenge in material science is to find new materials. And often what they have is billions of potential candidates, and they have to reach to tens of hundreds of promising candidates so that they can focus on those promising candidates to do further large-scale simulation and experimentation, characterization, validation, and verification. How to go from these billions to these tens of hundreds? Often it takes several years. But with the help of trustworthy AI foundation models, we can do that in minutes or hours. We take a large foundation model that is trained on very large corpus of material science data, right? And use that model and fine-tune that model on a particular class of material data that a particular scientist is interested in. And that will allow them to quickly filter through various candidates by predicting the properties in millisecond, right? So if we can predict the properties of a potential candidate in a millisecond, we can explore thousands of them in minutes. And then we can just go and sort and then say, like, which is better, and take them for further study. This is what's shown in the chromophore plot, where you have each dot is a potential candidate. And from those potential candidates, we went to these interesting candidates by predicting the properties of each candidate here. There are millions of them. We can predict the properties of each one of them and then identify what are all the promising ones in a matter of minutes. This is transformational for material science. We are talking about reducing the time to discovery from a decade to few months. Imagine if we can find new materials at that speed. That is transformational, from battery science to all the way up to materials for aeroplanes and so on and so forth. We have seen what extreme events, weather extreme events have caused in the recent days, Hurricane Helene and other extreme events, right? So how can we better prepare for such events? How can we protect lives? How can we protect properties? So to that end, we have been developing a foundation model for weather and climate. Here, the idea is to train a large model on a large amount of simulation data, which we have access to, the DOE has access to, community has access to, and then use that model to do weather prediction, to do climate forecast, and also, more importantly, fine-tune this model to do extreme event predictions. So we have developed models for various types of downstream tasks. But the base model, which we call Orbit, Oak Ridge Base Foundation Model for Earth System Predictability, it used 49,000 GPUs on Frontier, and we achieved 70% scaling efficiency. And we have exceeded 1.6x of flops in training. And we are finalists for 2024 Gordon Bell Prize for climate modeling. So more importantly, this kind of foundation model, when fine-tuned for various types of climate and weather tasks, can be used in a very fast way. So these models can act as a very fast surrogate for a computationally expensive simulation. A simulation that takes several weeks to run now can be run on a laptop in fraction of seconds. That is a very transformational capability to deal with extreme weather and related events. There is one thing about developing foundation model, but we are also looking into ways to establish trust in the AI systems, focusing on uncertainty, validation, causality, and privacy. To that end, we are developing foundational methods for these type of large models. One important capability is uncertainty quantification. This is how AI for science is drastically different from AI for commercial applications. Right here, whenever we get a prediction from a model, we need to have uncertainty as part of that prediction. Otherwise, scientists will not trust the prediction. It's not that the AI model is going to be correct 100% of the time. There are regions where it will be very good. There are regions it will be very bad. And it's important to assess the uncertainty of the predictions in the model. And we have to make that as part of the model prediction itself. So we have developed software algorithms for that uncertainty prediction and make it available, first of all, as open source for everyone to use, but also we are integrating that into various applications across ORNL so that when people develop AI models, they can use this method and software to bring uncertainty as part of their predictions. Uncertainty is not only about establishing trustworthiness, it also offers autonomous experimental capability in various experimental facilities. If we have an AI model that can predict the outcome of the experiment with a very high certainty, we don't need to run the experiment. On the other hand, if it has a high uncertainty, we can go and run the experiment and take the data and bring that back in the model and retrain the model. This can allow us to do autonomous experiments and, more importantly, save a lot of unwanted experiments and focus on the experiments that are absolutely needed. That is, again, transformational. Now we are talking about increasing the productivity at the experimental facilities by several orders of magnitude. Causal AI is the next frontier in AI. This is about figuring out what is causing what. In several material science problems, it's about, okay, we have the structure, we have the property, we need to figure out what part of the structure is responsible for this particular property. And that is an important aspect because it's not just about predicting the property, it's about understanding what part of the material structure is responsible for this particular property. And that can significantly improve a scientist's understanding of these materials. And that is really pushing the boundary of human knowledge, right? So that's a very exciting value proposition from AI. AI is not just about predicting, not about just generating something. It's about improving the human knowledge, which otherwise impossible because of all the complexity with experiments and high dimensional data and so on and so forth. We are also connecting large scale compute facility with the experiments. So this particular work is about running experiments at the experimental facility called Spallation Neutron Source at Oak Ridge and transferring the data to Frontier and train an AI model and then ship the AI model back to SNS and use that model while we are conducting experiments to predict the outcome of the experiment. And if you're doing well, then we can go and stop the experiment. We don't need to go and do further analysis. Now, team has shown that we can reduce the experimental time around 30% by doing an AI-enabled experiment, AI model-enabled experiment. We can save beam time. We can pack more experiments in the same amount of time and improve experimental efficiency, which ultimately results in new material discovery at a much, much faster rate. We're also doing AI at the edge. It's not just about always large models. It's also about tiny models, which are operating at the edge, near the experimental facility, near the experiments, near the instrument, so that we can do fast analysis at the edge. So here is what you see here is imaging and characterization. And by using FPGA and Jetson Nano and sort of using small models, we can do at the edge fast inference, fast analysis, and move the data to far edge GPU, GGX machine only when needed. So this results in not only in faster data analysis, but also a lot of energy improvements. On the AI security side, there is a significant effort, a very large effort at the lab. So the lab is very well known for national security research, in particular cybersecurity research. And with the AI, we are bringing the AI research and cybersecurity research at the intersection. We have this AI security research. There are two critical facets of AI security research that we are looking at. What are the threats emanating from AI system, and what are the threats to AI system? These two are really an important question when it comes for AI development and deployment, and how we are going to develop responsible AI systems, and also how we are going to protect our assets, which will be powered by AI systems. To that end, the National Security Directorate, in the National Security Directorate, we have this institute called CASER, led by Edmund Begoli. And this institute is looking at various basic and applied research and related methods to improve the AI security research. We are also bringing the world-class resources such as Frontier to analyze vulnerabilities of these models, threats, and risks that are related to security and misuse of AI. Technology is one part of it. R&D is one part of it. But it is equally important to educate and to create awareness of these advanced AI techniques across the lab. To that end, we have launched ORNL's AI Academy, and within that, we are running several different programs. AI Summer Institute, primarily targeting summer students. Tutorial series for science, primarily targeting researchers who are just getting into AI, but they want to experiment with AI for their workload, their science use cases. Yeah, for science boot camps, these are very targeted sessions where people who are already doing AI, we want to bring them together and use advanced AI techniques to bring secure, trustworthy, and energy efficient AI to their existing AI workflows. AI workshops, AI expos, and seminar series are other mechanisms that we use to educate and to create awareness of advanced AI techniques. Really excited about FAST. So FAST, it stands for Frontiers in AI for Science, Security, and Technology. It's a Manhattan project for AI from DOE. It has bipartisan support. The labs are all 17 labs coming together along with academic and industry partners to really define the next frontier in AI for science, security, and technology. There's still work in progress. There's an ask, there's budget request, and so on and so forth. Despite all the usual things that we have to do to make this program real, it's important to note what this program means for science and security and energy. So there are several interesting ideas and research directions that were discussed in these two reports. I highly suggest the viewers to look into these two reports for research direction, like what does AI mean for science, for energy, for security. It has 4 pillars. FAST will build the world's most powerful integrated scientific AI systems through 4 interconnected pillars. Pillar 1, AI-ready data. Make the data available within DOE as ready for AI. Pillar 2 is frontier scale AI, computing infrastructure and platforms. And pillar 3 is on safe, secure, and trustworthy AI models and systems. And pillar 4 is about bringing all these to applications in science, in security, and in energy. Currently, there is a notice of request for information on FAST initiative. So this is primarily for industry and academia. Anyone can respond. And this is about in what ways industry and academia and other partners, other agencies can engage with DOE under FAST, and how transformational such a kind of collaboration will be for the nation. So I please look into this RFI, and I highly recommend you respond to the RFI. I want to end my presentation with a couple of high-level thoughts. The first one is based on Michael Levitz, a professor at Harvard, who studied physics, mastered biology, and won Nobel in chemistry. There's a podcast which is also available on YouTube. I highly recommend the viewers to look into that. It was talking about how AI is going to change science and other domains forever, right? So that's the kind of impact that these AI models are going to have. And he was giving the example from his own life, right? So especially how he managed to bring together insights from different domains and make discoveries. And such a kind of technology or such a kind of insights is now available, now can be made available through AI. Now that can be made available to every scientist in the DOE complex, every scientist in the nation. Think about the potential of such a kind of technology for scientific discovery, whether to discover new medicines, to address climate change, or to come up with better materials for battery. So many things. Finally, we cannot end the presentation on AI for science without the recent Nobel Prizes, which actually define the new interdisciplinary research. FAST, AI, technology, those are all amazing things, right? But what I really think AI will do is to bring or to define new interdisciplinary research, as which was evident in this Nobel Prize, in these Nobel Prizes, right? So the people who won Nobel Prizes, very, very interdisciplinary. It's not one particular field. It's a mix of multiple fields, and AI is a catalyst to bring people from different domains and to make connections between different domains, and particular make the knowledge that are from different domains to be accessible for everyone. And that's the part that I'm really, really excited about, and what it can do for scientific discovery. It's going to be amazing, and I can't wait to see. Thank you.
Thank you, Prasanna. That was outstanding. Really enjoyed it. Your opening slides on the history of AI, always enjoyable to be reminded that oftentimes things in science go much further back than we think. And certainly that is the case for AI. I really enjoyed learning about all the things that are going on in the laboratory. I'm sure our viewers who are interacting with those domains will have a great deal of interest in those outcomes. Really incredible numbers. Always think about the supercomputing at Oak Ridge, and the capabilities of high performance computing is really changing the arc of humanity in many ways, and really accelerating us in ways that we didn't think was possible before. I wrote so many questions down here. I don't think we're going to be able to get to them all. One of the things that I wanted to go back to, since this is, I'll start with a few questions based on your presentation, and keep them at the top level. So this is, we are the Government Activities Committee, and so one of the things we think about is policy makers' trust, the public's trust in us. And I noticed, I think it was slide 15 or so. I've noticed scientists, we think a lot about trust, and we map pretty quickly from there to things like uncertainty quantification and causality and these very abstract things. And I'm wondering your thoughts on how do we, it's, I think to really appreciate and to find a sense of trust in those trust apparatuses, the uncertainty quantification, causal reasoning, privacy preserving, you kind of have to have a technical knowledge of what those mean, right? Sometimes policymakers may not, or the public, is once removed from it. What are your thoughts on our ability to make sure that there's a trust language that gets to non-technical people?
Fantastic question. So I can speak that from my personal experience because I'm involved also on the other side, helping policymakers to see through some of these technical challenges. Of course, there are several barriers, right? So clearly, communication gap, right? So policymakers often do not have the technical background, and the technical jargons and complexity can create a big disconnect, and there is also nuances and sort of implications of AI advancements. So this is clearly a challenge that one need to take into account, right? So how can we make this communication gap narrower? The second thing is the pace of AI advancements, right? Even as an expert, it's very hard to keep up with the advancements of AI. Okay, at a very high level, things are probably going relatively slower, right? Or it slowed down in recent months, okay, recent years. Um, but we have to, at the same time, it is important um, to to make sure that these advancements and capabilities, and also the potential risks with these advancements, right? So these need to get into the policymakers, and they are not used to this kind of rapid advancing technology and how to grapple the complexity with that. To make matter worse, as AI experts, we don't know sometimes what the potential complications are. That makes this much more challenging, right? So it's it's sort of like, it's we need to understand this in a much better way to help the policy makers, but at the same time, we face challenges as well because of rapid AI advancements and the complexity and the sheer size of model, AI models that are very hard to validate and verify and see through what the models are doing. Um, and non-technical stakeholders, they're also very wary of AI capabilities, right? So given what goes around in the newspapers, right? So often, there's a good thing versus bad thing, right? So the bad things are picked up much more easily, and it's sort of make it to the headlines, like bias, misuse, and security vulnerabilities. I'm not saying that those are not existent. Those are really true and part of it. But also, it's important to understand, sometimes the policy makers can be misinformed by this news. Sort of like, oops, AI bias, bias and misuse and risks and things like that. Yes, we have to address that problem, but the thing that we are going to get out of this technology is 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 amazing, right? So we cannot leave that out. So we need to have this balanced view of what are the potential opportunities and the risks associated with the opportunities, and find a way to carefully manage the risk and maximize the opportunities.
It warms my heart, Prasanna, to hear that you too also struggle to keep up with everything that's going on. I worried it was only me. Interject an anecdotal story of my own here very briefly. A few years ago, I gave a presentation to a real decision maker. A decision had to be made with high consequence, and I stood up and gave all of my best slides on the uncertainty quantification, we did, Monte Carlo sampling across parameter spaces, and translated that into uncertainty in the decision space. And I said, and therefore, there's a certain probability that, and this guy, I'll never forget, stood up and said, but do you think the numbers are right?
Hmm.
Talking to me. And really, it took me back a little, but if you think about it, what he's really asking is there a trust in the institution? So,
Yeah,
so I think it will probably, it's very important to maintain and demonstrate a basis for trust in institutions.
yeah,
I often think about I'm not sure if I can say the name of the cars or not, but I got a sedan in the garage and it's very reliable. I really don't know how it works, but I know that I mean, I can change the tire, I think, but I just know the company and they're very reliable in all the material sciences and the physics and stuff and the engineering that goes into that combustion engine and forget about it. I just trust them. So I think that there is an element of that there as well.
yeah.
Um, yeah.
So to that end, I think we could do better on bridging this technical and policy worlds, right? So, structured interactions between scientists and policymakers, and that's where, IEEE and CIS can play a major role. Definitely help to bridge these two worlds and have regular structured interactions, workshops focusing on AI policies and so on and so forth, especially emerging technologies and whatnot, right? So this is something that IEEE can help with.
yeah, that's a great point. Yeah. I mean, I think that's the reason the Government Activities Committee has been formed. Uh, some folks at IEEE recognize this, and I appreciate them thinking about it. Let's talk a little bit as well about the other side of the coin. Too much trust. Uh, I found myself, even a scientist working in this space, to become sometimes a little lax with Chat GPT. Especially, I've learned to use it for like home improvement and things like that. I just want to know I want to know how to change something in my car. Especially the new voice activated. I think ChatGPT 4 or something has that. You almost just have this conversation, right?
Yeah.
And during the conversation, it's easy to become lax in your judgment and your being due diligence and remembering this is a formative product. Do you think that the public I think the public needs to be careful about familiarity. Your thoughts on that or
Thoughts on ChatGPT in specific,
Not
or
ChatGPT specific, but just in general, too much familiarity with these products gains some trust that maybe I think that that's a risk of that as well.
absolutely, absolutely, and as part of my policy engagements, this is one of the key thing that we are taking on, right? So, how to ensure responsible use of AI. So we are not against using AI, but we have to find out either in education, government operations, state operations, and I mean we know we have a good handle on scientific applitions and national security on the research side, but when it comes for deploying these and bring it to the 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 applications outside of this research world, right? There are a lot of things that we need to take into account, and it's important to help the policymakers to see through this, and also being transparent about what this technology is about and where it can fail and what the limitations are and what are the potential dangers and of this technology. So education here goes both ways. In particular, we need to provide a balanced view of potential opportunities and also educate them on various types of risks. What are the potential consequences if things can go wrong? And for this class of applications, right, should not use, or you have to have a human in the loop, or we even think about AI as a sort of a supplement to that as opposed to replacing something, right? So there are, it's not one size that will fit all. That's why it's important to sort of, look at classes of applications or case by case basis to see what is the right way to use AI,
Yeah.
and also communicate and educate and create awareness about this technology on both sides, right? Okay, don't need to be afraid of, but at the same time, you have to be afraid of certain things, and these are the potential consequences,
Yeah, and I
unintended
think
use
even at an
cases.
early age, I could, making a leap of assumptions here, but I can easily imagine that we could see that it would be important for courses to be taught in AI use, consumption of
Yeah.
AI, even in middle and high school, and how do you really use these things and maintain awareness of them and responsible use of them as part of the core curriculum. It's not my field of expertise, but I would not be surprised
Yeah,
if
I'm talking, I had conversations with Oak Ridge schools and Farragut schools here. Um, One thing that I learned is students are much more faster in adapting AI compared to TI.
yes, I have
That's a
had a
problem.
similar experience.
That's a problem. So, and that has consequences, right? So we already see the consequences of it. So that's why it's important to create awareness and educate the workforce, both the students, teachers, and users, developers, and stakeholders, right? So all the stakeholders. So it's we have to, we are just getting started, right? So this is amazing. We're just getting started. There are a lot of things to be done, a lot of work to be done, and it cannot be done by single entity. We need an all hands approach, specifically, government helping us in various kind of things, and we help the government in various policy related things. And we should not lose the potential, like what the opportunities that emerge from AI. But at the same time, we have to constantly think about the risks of AI and find ways to manage it in a responsible way.
Yeah, I saw a webinar this week from AAAS, and it was about one of the speakers was talking about a challenge being that scientists in this bridge right between science and policymakers or science and the public. And interesting, I'll find the link for it and put it down below here. But they were talking about, scientists are apprehensive to talk to policymakers, apprehensive to talk to public because they're not sure, they feel they don't understand the implications of things they say, and maybe they say something that's taken the wrong way. Do you ever have experiences with, do you have any advice for scientists? I think you're dealing with some people in policy, and any words of wisdom for us?
Absolutely. So, I serve as a member of AI Advisory Council in the state of Tennessee. I work with wide range of people in that effort, and it's fantastic thing that state came up with this AI Advisory Council where they brought diverse set of people, not just AI people, but diverse set of people to this council. End users, applications, and government operations, state government operations, and experts like me. And we are really looking into, what are the ways that AI can benefit the state, and what are the ways that we can minimize the misuse of AI in the state operations, and so on and so forth. How can we help um, people in the state with different types of AI technologies? How can we help industries, manufacturing, healthcare, transportation, and other aspects? So there are many different things that we can help with, but at the same time, when it comes for risks and biases, these are things that need deep technical knowledge and expertise. And first of all, we need to understand that. And the second thing is how can we manage that? And third thing is how we can reduce that, right? So there are multiple facets, and this becomes research problem, and this becomes more a research program to look at various aspects of it. But my suggestion is, as a scientist, I think it's my responsibility to engage with the policymakers, especially in AI. We cannot refuse, or we cannot stop talking to them, because this is a technology for people, right? So we are in a point of civilization, right? So prior to this and after this, right? So that's the kind of impact that we are going to have. And I think a lot of things are at stake, And it's important for scientists to engage with policymakers and help them help them navigate this difficult terrain. And it's not just difficult for them, it's also difficult for us. That's why it's not just me, right? So it's a community of people. I can be wrong in certain things, but if I bring hundreds of other experts and I can go and talk about this with others, the probability of making a mistake will be much smaller, right? So
Yep. Yep.
as a scientist, I admit that I don't know everything, and I will rely on my colleagues and other experts and so on and so forth. So, but in any case, we should not stop engaging with
Yeah.
the policy makers.
Oh,
I think it's a very, very important thing. Uh, it's very critical as we move forward.
yeah, they're going to have to make decisions with or without us. We prefer
Yeah.
that they make it.
Imagine that scenario. They
Yeah.
make decisions without us, right? So
What is the
that's
worst mistake? To not be present. That's the worst mistake.
exactly.
Well, we're coming near the end of our time. I wish we could go another hour with this. It's really, really interesting to hear from you and your thoughts on this. But let me ask you, how, if someone wants to work at Oak Ridge, a student wants to get involved, what should they do? Can you say a little bit about that? How do they connect with you and others at the lab?
There are various programs to work at Oak Ridge, starting from even high school, right? High schoolers come to Oak Ridge in summer to do projects, and several high schoolers came and did projects in AI last summer, and it's we have a high school program, and we have undergraduate program supported by funds, by project funds, and also we have undergraduate program called SULI from DOE. It's a DOE funded project,
Awesome.
and we have the summer student program, and AI initiative has a AI Summer Institute where we bring summer students and sort of create a community around AI every summer. And it's not just about working on one particular project. It's also about creating this network of people, so that even after they leave, they are in touch with each other and think about collaborative projects and come back to Oak Ridge after. We have postdoctoral programs for PhD graduates, and there is a usual postdoctoral program. There is also named fellowships, which are more prestigious, where this applicants need to write proposals, go through grueling set of interviews, and emerge as a winner. So these are very, very selective, very competitive, and these are really, people who get these fellowships. They often become the next leaders defining the field. We have software developers, right? So software developers in AI projects, need for software developers across the board, and we have such questions across the lab. And scientists, early career, mid career, scientist questions, they're open all the time. And FAST is a platform that we are planning to use when the program comes in, to hire students, and software developers, researchers, research scientists, and so on and so forth. So there are many, many different opportunities. Oak Ridge is a very, very unique place, when it comes for compute capability, when it comes for science domain expertise. It's amazing, how all these things are available in one place, right?
Yeah,
So
crazy.
it's very hard to find such a place where people can work on cutting edge problems that matter to the nation,
Yeah.
matter, that solves world problems, world challenging, problems that we face, um, climate change, new battery materials, and so on and so forth. Right? There's so many things to do in the lab, and AI is integrated everywhere. It's very hard to find a directorate, a division, or a group without AI, these days. So a lot of opportunities. I'm happy to help making connections in one way or the other. So please feel free to reach out to me.
Very generous of you. I'm going to put you on the spot. You don't have to provide an answer, but as a thank you for being here today and speaking with us. who would you like to see us host next for a webinar? An institution or a person comes to mind that you would like to see us interview or have a webinar?
Oops. I have like 100 people in my list. Much better than me. So I will send you recommendations
Awesome. Yeah.
on that. And if you get any of the Nobel Prize winners, that would be great.
I
So,
will. We'll have to get some more qualified than me to host, I think, a Nobel Prize winner.
but there are so many amazing people across the DOE complex, across universities, doing amazing work. They inspire me every day, and I'm happy to send a bunch of them.
I'll take that. Thank you. Well, I think we've come to the end of our time. So we've mentioned a lot of things in this talk. I think there's Oak Ridge National Labs, there's the FAST DOE thing, there's a podcast that Prasanna mentioned, many other things. We'll provide links to those in the notes and maybe some other things that are useful. I think any last word, Prasanna? Anything I've missed, or I'd keep you for
Uh,
an hour.
yeah, as a closing thought, AI is at an inflection point, and national labs such as Oak Ridge are advancing and pioneering scalable, trustworthy, and energy efficient AI for science and national security. It is essential to seize this moment and build strong collaborations between technical communities, policymakers, and global institutions. So this is my message to the community, and really grateful for the opportunity. And thank you.
Couldn't think of a better note to end on. Thank you for that, Prasanna. So with that, we'll close out. This is a Computational Intelligence Society's Government Activities Committee hosted webinar. If you're interested in any of these things, they'll be in the show notes. Everyone have a great remainder of your day, and we will see you the next time.